multi-year Lean and Six Sigma practitioner. Through his career, he is certified as a Master Black Belt, Champion, and a Yellow Belt, along with teaching and certifying professionals in all the Lean Six Sigma areas. His personal Lean Six Sigma work has spanned nearly all business types: manufacturing, transactional, along with research and development business. He is a master degreed statistician and has taught statistics in the Penn State University system. He has worked in all levels of the business, from the entry level up to site engineering manager. His life experiences and skills will provide you with an engaging discussion on binary logistic regression. I will now turn the webinar over to Rick, and we will get started. Thanks again.
Hello, everyone. Every time I listen to that about me, it makes me think I've been to school too long. Thanks for joining us. Now, who would have thought you'd get an engaging discussion of binary logistic regression? It almost doesn't fit. But let me talk about the company I'm with now. It's Smarter Solutions, located in Austin, Texas. It's been around for 17 years right now. Started teaching Lean Six Sigma. It's gone into a really what we'll call the integrated enterprise excellence system, what we teach now. It's a method of using the Lean Six Sigma tool for really business improvement, not just the plain Jane Lean Six Sigma. Pretty neat stuff, but it gives me the chance. I'm an instructor primarily for Smarter Solutions, some level of consulting, but it lets me spend time doing webinars like this on topics I really enjoy. The first question we have here is I'm trying to get to decide where people are and somewhat why you chose to go to this webinar. Are you just interested? Is this just continuing education? Or are you just looking for ideas? Please select one of the choices on there. We'll share the results with everybody when it's done. Looks like they're coming in. Looks like we've got interest and opportunities to advance, so it's good to know. See how we should be just about there. How about we'll close it in a few seconds. There we go. It'll pop up on your screen now, and it should say, most people are trying to advance their personal skills and just general interest. Well, let me tell you, the webinar will allow you to advance your skills. We're going to teach you how to do this. I guess we're going to go. All right. Here's our agenda. We're going to talk a little bit about how binary logistic regression works. It is a very special tool that they don't talk much in black belt training. I think it's not in the body of knowledge. We'll ask you about what you think about it towards the end. We're going to work out two examples. Now, I'm going to use Minitab to show you how it works, but it should work on any real statistical software package. JMP Jump does it. If you're a SAS user, it does work. And I assume SPSS and all the other ones will also do it, but I haven't tried them all. I choose Minitab because the majority of the Lean Six Sigma providers do use Minitab. Probably JMP is the second choice. Then when we end, we'll talk about logistic regression other than binary, which is the ordinal and nominal. And then I have bonus topics. It's not really much of a bonus, but it is part of the fun you get when you learn how to use a tool, all the other ways you can use it. So to start off, if you've never seen this, don't be scared. This is only a slight extension to what multiple regression is. You'll find where we're going is the magic of this is it converts the attribute to continuous, then just does a straight-up regression. Now, the reference for this book and the examples I'll be working through are in Forrest Breifogel's volume 3 of his 4-book series. Now, I know the first book has not a volume number, but this is it's as much a text as a reference to running improvement projects, the Lean Six Sigma types. Covers the soft skills, the lean skills, the Six Sigma skills, plus a lot of statistics in it. But that's where I'm extracting this from. Now, when should you use logistic regression? Well, you need an attribute output metric, or like your project metric, or the only data you have on successes is a pass-fail data, or it could be nominal data, colors, categories, or it could be ordinal, which would be like Likert scores, what you see for surveys and such as that. Any one of them you can use. But you use this when you have continuous predictors, or X's, because we already have tools if they're all attributes. But when you throw in a continuous one or two, it becomes more difficult, and that's what we're going to talk about here. All right. If you have only attribute predictors and an attribute metric, generally would use the chi-squared test, also called the chi-squared test of independence, sometimes a table test. But that's the best choice if they're all attributes. Now, where could you use it? Well, here's a couple examples I've seen through students coming through evaluating health insurance claim rejections. All they know is the claim either made it or it didn't, and they know possible reasons, the dollar value of the claim, the type of the claim, who did it, what region, what time of day, such as that, a mixture of continuous and attributes. Could be in a manufacturing quality problem. I did a consulting job up for a company up in the Northeast about making semiconductors. All they knew is when they plugged them in to make them work, they either worked or they didn't. There wasn't any continuous measure of it, but they knew all of the manufacturing parameters, the temperatures, the pressures, the raw material batches, and all that, and we could resolve where the problems were coming from with this tool. Last one would be customer voice things. Any Likert scale data, customer surveys. You can do it by type, by dollar value, by age of the person, by the amount of sales or whatever, but you're trying to predict the results of Likert scale or any scoring. So these all would work. Think as we go through the seminar, as Mallory had asked you to type stuff in the GoToWebinar interface, I'm going to ask at the end questions that I haven't covered, but also examples where you may have used these tools or think you might be able to use these tools. Now, this is from our hypothesis roadmap for our Lean Six Sigma course, but it talks about how things work. Now, what we have is a hypothesis test. Binary output is what I'm talking about now. Inputs could be continuous or discrete and be binary logistic regression. I find that many of the hypothesis roadmaps I've taught with, this is probably my third place I've taught Lean Six Sigma, didn't even have logistic regression on their roadmap. The two we'll talk about towards the end are the other two choices when you have two or more output levels like Likert scale or ordered data, or just nominal, such as colors or categories. The second question comes up now. I would like to get a feeling for your level of knowledge about logistic regression, binary or otherwise. And you can go from you've never heard of it to the bottom one, you could be teaching this instead of me. So please check where you are on that. You get one choice. Good people are responding. I was expecting most people knew it existed, but have never tried it or never been shown how. But it looks like a majority of these people have used it. We'll see how you all score, but would like to get better at it. Well, great. We'll close the poll off here in a second to see. There we go. You should all see it now. Majority of you have used it. That is surprising. That is excellent, actually. So now if I would get better questions, I assume, if you've used it. But also it means you'll hear from people if I'm telling you a straight story. All right. Let's move on. Thank you for that. Binary logistic regression. Most common one, the binary means 2. Your results are pass-fail generally. Now, the magic of logistic regression is that it takes the attribute score of defect rate, or percentage in this case, and converts it to a continuous variable. Now, the equation is shown on the screen. They're called the logit function. It's the natural log of the p over 1 minus p, or q. Now, what it's really doing is turning continuous into discrete. And I'm going to do a little diagram of it here. Oh, just a second. I did forget something I was going to do. Just to show you, this is me. You should be able to see on your screen. I'm sitting in my office right now in Austin talking with you. It's not a great picture, but you don't have to look good to be a good practitioner. Let's get back to the presentation here. What I'm going to do is I'm going to go show you how this really works. A little whiteboard software makes up for the problem when you do webinars is you can't turn around and draw on the board. Well, let's do first a diagram of what happens. When I have P, I'm going to make a little chart where I really have 0 and 1. This will be my P. And this is the x-axis. When I plot P, as it goes from 0 to 1, it looks like this, where this goes from 0 to 1. Linear function, but note, it does not exist greater than 1. That's a dotted line. It does not exist less than 1. That's why regression won't work with percentage data. Now, early in my career, if your percentages are somewhere near half or in the middle, you can get by with regression. You can get by with ANOVA because they can be treated as virtually continuous data. But when you get close to 0 or 1, it all falls apart, especially if you've got a batch with 0 defects. And really, logistic regression came into my use when I started getting better quality to the point that I couldn't get by with the continuous approximation. So then we look at the logit function. The next one is P over 1 minus P. Now, what's that plot out as? If I do another plot, what I have here, I'll put P again at 0 to 1. Well, when P is 0, what happens here? It's 0 over infinity, which is still 0. So I start out here. And what happens when P is 100% or 1? Well, that should be a little P at the bottom. This goes to 0 on the bottom. We know that goes to infinity. So the plot looks like this. And as P approaches 1, assume there's a dotted line, it asymptotically reaches infinity. But I still can't use regression because I still cannot have a value of less than 0. That's why we go to the natural log of P over 1 minus P. Where'd my P go? There we go. When I plot that, it looks like this, where here's 1 and here's 0 again. Somehow I'm erasing my own here. Let's see if I can make it stay. There we go. But what's going on is this goes to minus infinity to infinity now. Now what I have is a continuous function. As P goes from 0 to 1, it goes from negative infinity to positive infinity. Once I have this equation and it changes its function, I can now use general regression. What this can tell you is actually, if you wanted to do this math by yourself, you could create this logit function and just use the normal regression tools. But in reality, Minitab will do this in the background for you. So let me go back to my slides. That logit function is called the link function that maps the discrete into the continuous function. Here's what it really looks like with better graphing. I used Minitab to draw that graph. But again, the logarithm takes the numbers from 1 to 0 and stretches them out to negative infinity. So we have a continuous function here. That is the requirement to use regression. So we're all set. Now, there are other link functions. Minitab uses 3, but I know from my school that there's a lot more than that. The question is, which one should you use? And I'll cover how you choose it in a little bit. I guess I really won't, but logit is the most common function. It's the default Minitab. It's the default in the training I got back when I got my degree. And you start there. But the question is, when do you use the other ones? I remember being taught, well, you use the one that makes the most sense. Well, but even to this date, I've been doing this a while. I don't know what makes sense other than logit. But the best guidance I can give you is in the bottom bullet there that says you try the other link functions when you fail the goodness of fit tests in your assessment of the output. Now, we're going to use the goodness of fit test like we would the goodness of fit or the normal requirement for a residual and a regular analysis. But I'll cover that piece as I go through how you do the analysis. But generally, logit is the one everybody uses. You get slightly different answers depending on which link function you use. But I found generally the decision of significance or not, which is what the Lean Six Sigma is looking for, all of them seem to give me the same answer in the cases I have tried it. So how do we determine what X's are significant, what parameters? Well, it will give you a p-value just like all the other hypothesis tools. So if you just care about significance, I'd say you can treat it like a black box. You put the stuff in, hit the button, look for the p-values, and decide significance. Now, that's good enough in many cases, but if you want to take it beyond that, we're going to be talking about it here. You can actually make some level of prediction with it, too. Now, the first thing, like all regressions, once you do it, you get your parameters and your coefficients and your p-values. The next question to ask is, did I meet the requirements of the regression so the fit can be considered good? If you have not heard it this way, but regression and ANOVA and design of experiments and others, the assumptions to the ability to use the algorithm are that the residuals are acceptable. They don't say anything about the original data. So in this case, again, we have to run the logistic regression and look at its output to see if we met the requirements to use the answer. Now, because of that link function, it is not as simple as a normal residual and the simple 4-quadrant plot Minitab gives you, or what you might have been taught. We're going to talk in a minor case about 2 ways to look at the goodness of fit, residuals, and high leverage points. Stuff would normally be flagged as an unusual observation for investigation, but it's not as simple. Now, there's lots and lots of options, and I know different practitioners have preferences. We're going to talk to only 2 as we go through here, which I have found that has been good enough for me. Okay? We'll talk about a Pearson chi-square goodness of fit test, which I'll talk about when I get that slide, and we'll talk about 2 charts coming up. Now, with the goodness of fit test, generally I think Minitab gives you 3, and in some cases it'll give you up to 5. But in the nature of this fit, you can consider that if any one of the goodness of fit tests is adequate, you can move on. If all fail, then you should stop, and that's when you consider the other link functions. Now, I know I haven't showed you one yet, but we're getting there. Now, for outliers and good and unusual points, there's a number of methods. I think Minitab gives you 10 different charts to look at. We will talk about 2. One's a delta chi-squared versus the predicted probability. It's a neat one because what it really does is it pulls out each data point, does a goodness of fit test, and looks for changes in the goodness of fit. So you look at the magnitude of change of how well it fits. Anyone that changes the fit a lot is probably a high influence point, and it works out pretty good. Now, one of the toughest parts of this, and once you've got your answer, you can actually write a regression equation just like you'd expect. I'm going to use one of the magic little tools here. This is your regression equation that comes out of logistic regression. Just like you'd normally see, the problem is it isn't predicting probability. It's predicting its logic function. Now, what's difficult, depending on your math skills, solve this for P. Well, we've given you the equation here. That's the equation. Now, you don't have to go run and write it down. After the webinar, I will send you the files I used for my 2 examples, and these equations will be on a tab on an Excel worksheet. So you'll have these after the fact. Now, what we're talking about is EPRO, which means the expected probability. Don't know if that's a common term. I know that's one Minitab uses to generate what it predicts every observation should have come out in the long term. You'll find where we're going is to save this jump of back transforming or unlinking, if you want to call it. We're going to use this equation. It'll give it to us. Minitab will generate this number for us. We'll go to contour plots and such to interpret it. I find that that's the most common thing people do. All right? It didn't give me. There we go. Next question might be, what's the data have to look like? There's really 3 formats that are common in this, and Minitab accepts all 3 of them. We've got the first one, which I have used almost only this, where you put a set of combinations. This is generally either your batch settings or even if it's a design of experiments. These factors, and of this one there's 20 total run, 19 passed and 1 failed. But again, they don't have to be common counts. This one here is a total of 13. But this format, you get pass-fail data. That's common. If you get outputs out of many quality systems, you get this. Here's my factors. And this piece was either good or bad. All right? So this is the longest data. So those dots aren't really dots. I mean, there's more data between them. The third choice is this one over on the right, where really you have one row for all the fails and one row for how many passed. So you tell it the response and get a frequency count. Three different methods. I am showing you here that you can have discrete factors and continuous factors called covariates. Now, covariate is the term for a continuous variable used in analysis of variance, but we will use that also for this function. So again, you can put in any of these methods. They all work. You just have to make sure you enter them in Minitab properly or the other software. Here's the test we're going to run. This data set really originated from the SAS software. It's one of the examples they used. It's a really nice one. And again, I will be sending you the data. What we have is it's a metal rolling process. They have to both, it's got a heating and a soaking setting on their equipment. Not too exactly what it means, but they're times. How long do I heat it? How long does it soak temperature? And then they roll it. Now, when you roll metals, if you don't get them to enough temperature, they end up, crystal and structure breaks. If you get it at the right level, it will nice plastic deformation, and when it cools, it's still got all its good mechanical properties. So in this case, we've got 19 different batches of material that had a setting for heat and a setting for soak. Now, these are continuous variables, even though by observation you might see that this is a full factorial of, I guess, 4 heats and 5 soaks, but it didn't have to be. You can note that all of the combinations do not have the same number of samples. Like sample 1 was only 10. But if I look at sample number 8, there was 31 samples that were ready and 2 that were failed. So there was 33 there. No, you do not have to have equal sample sizes. Now, it's always a benefit to have good equal sample sizes. Same as for regression, you'd want data across the whole range of your data. This is equivalent to having a whole bunch of data at one part of my regression and very little on the ends, which does lead to leverage issues, and we'll see that in this data. All right? So here's how to put it in Minitab, if you happen to have Minitab. But all software will come up somewhat the same. You've got, this is data entry here. Now, of my methods, the bottom one is when you have a table of pass-fail data. The upper one is when you have either the responses alone or the response plus the frequency of it. Now, in this example, I've got 2 factors that are my predictors, heat and soak, both continuous. Now, the graph I recommend doing, one we're going to talk about here is this delta chi-square versus probability. And I'm going to have us all save the event probability down here. We're going to use this data here to do our response surface, so I don't really have to back calculate everything. Now, it will give you residuals in the true sense of residuals if you want to look at them, but I generally find they match these, and this has got a little bit more advantage to it. But I would never recommend not looking at more and more diagnostics if you want to take the time. Here's what the output looks like. As I would tell a student, once I got the data in right and it didn't give me an error, I look for p-values. And what do I find? What's significant? The constant, the heat value, but soak is not. So it looks like the heating step is more important than the time it soaks. Great. Okay. Now it's even got, as you can see, coefficients. So I can write an equation. I can see that this is, I write my equation with these right here. Great. If you scroll down your output, you get your goodness of fit test. Now, the one I prefer is the Pearson method because that is equivalent to what we do with correlation coefficients. And it's got a chi-square value. And what you're hoping to see is that the p-value is greater than 0.05. I treat this as a probability plot p-value. Your base assumption is it is the right district. The goodness of fit, the residual is what it should be. And I'm looking to reject my null hypothesis. So if that number is less than 0.05, I'd reject the null hypothesis, which means the goodness of fit is acceptable. Now, most times all 3 match, and since all 3 of these have slightly different algorithms behind it, it's a reasonable practice to say if at least one passes, you're acceptable. Now, again, if you want, you can try the other link functions and see what that changes on the goodness of fits. I need to pick this time up. I'm rambling. Now here's the delta chi-squared versus probability. You note 2 points diverge from the rest of them. If you highlight those, that's rows 8 and 12. And when you look at these in the data set, they have the higher defect rates. So I would want to investigate them to make sure that it is not a special cause event. It is actually just part of the process. If it is, you go along and use the data, like all residual analysis. Now to make a contour plot, you take the output of the logistic regression expected probability. So what it did is it gave me one value for every one of my rows, because that was a set of conditions. And you get a probability plot. And this, as you can see in it, in some sense you would ignore non-significant parameters, but as you would in a response surface, you leave them in to get good plots, because I need 2 of these to get this plot. But as you can see, as I go up slope, there's very little change in the success rate. And if I look at the expected probability, I want this to be as small as possible, so it says I want to be in this zone. So again, looks like if my heats are less than 20, I'm probably okay. Now, I can also make a surface plot. I personally don't use these much, but some people like them. Same concept, and you get a surface plot. I guess from hiking and stuff, I like contour plots, but you can choose the one you want. All right. That was that example. That was a simple 2-parameter one. If you have questions, I guess Mallory hasn't shared any, so I must be answering them. Please type stuff in. If you want me to go back over something, that works too. Next one, example 28.6 out of that volume 3 textbook. This actually came from one of our students. Did it back at his office. We've cleaned it up a bit and got his permission to use it. What he was doing, it was an organic coating that they're applying to a fabric that it needed to pass a film hardness. It basically was a pencil you press down and draw on it. And given the result, you decide if the coating is acceptable or not. They had 3 factors: the percent of the organic coating in the solution. They had a pencil hardness used, 1 to 3, hard to soft, and then they went through the pressure that the person would write on it. Now this is a human test. They grab a pencil, they draw on the edge of the cloth to see if it's an acceptable coating. So of controllableness, they can control the coating setting, they can control the pencils that are available, but it's awful difficult to control how hard somebody presses on the fabric. Now here's my data. Same format of the last one, number of passes, number of trials this case, so 10 out of 10 or 0 out of 10. And then my 3 settings. Note again, this happened to be a design of experiments type setup, but it still is just data. Now, here's where I entered the data. Same 2 plots. All my p-values are significant. Therefore, all 3 of these matter. The question is, what should I optimize to? With my goodness fit test, 2 were acceptable, 1 failed. I would consider that acceptable to move on. My equivalent of an outlier analysis, none of the data points are wildly diverging from the rest. I'd consider it acceptable. I would now use my result, put my expected probability in for my contour plot. But now wait a minute, I got 3 factors, and I don't know of a good 3. I need a 4-dimensional plot to do them all. So instead I'll do 3 2-dimensional plots and look at the results. Now if I look at my expected probability, I want the test to pass 100% of the time. So I want both a setting for my process, which was the percent organic, plus the testing characteristics so the test passes. Now this is, believe it or not, an ASTM specified test. It's not one they made up. So if it passes the test, the quality is considered good. Now I look at this, the organic coating, it looks like the more I have, the better I am, the darker color. So you want to be up in this zone with less pressure. Makes sense? But again, more coating costs more money, so I don't want to necessarily just pump it up all the way. Now if I look at the other 2, when I compare the pencil hardness to the pressure, the 3 does better than the 1, which a 3 is the harder pencil, with pressure lower. All right. When I compare coating to the hardness, again, at least it gives me that the number 3 is the better pencil, but also more organic coating is preferential. Now when you lump all these together, they actually took the equation out and solved it, as we showed in the earlier equation. but they found, I guess, softer pencils are better, more coating is better, and lower pressure is better. So what they did is they took the model and solved for it and found it when they used 10% organic, and they used the number 2 pencil. They had a 67% chance of passing. But the passing went to 100% if they used pencil number 3, even at the hardest pressure. Since pressure was the one uncontrollable function they optimized to, the second case, so it would always pass no matter how hard the people pressed. They solved their quality problem and started shipping 100% until they had a process failure. So again, that's how you could use it. This would have been extremely difficult with standard regression. I did coach this gentleman. And when you get 0 out of 10 and then 10 out of 10 with those numbers, you can't really do regression any longer. Now, there are 2 more types of regression, nominal and ordinal. Nominal is where you just have categories, colors. If you want to distribute the states, I had one of our students working with delivery or where defects were coming from. It was a military one based on location in the world, and all they had was location. There wasn't order to it. They were just different. They ended up using nominal logistic regression. There's also the ordinal case. Ordinal numbers means they are numbers, and they have order, but the differences between them are not necessarily the same. Likert scale is one, which you have the 1 through 5, or very negative to negative, the neutral positive, and very positive. So you can talk about trends in that case, but you can't really use it. They're not really continuous data. Both will work. If you need to use them, whichever software, all you have to do is figure out how to get the data in the right format. It will give you a p-value, if it's significant or not against that rating. And the one real difference that I've noted running these is you don't get such a pretty equation for what the answers are. What you really get is you get the ability to predict, and with each set of predictors, the probability of getting one of the answers. If I had, go ahead.
Rick, we had a question.
Oh, go ahead.
What is the number of trials for a valid analysis?
Wow. In my experience, it's all you can get. Now, there isn't a direct number I can give you. There is no sample size calculator like you have in t-tests and such. But like this one, we had added samples. They did 10 in each one. And I think there is I don't know for the whole test, depending on what resolution you want, you need more data. But as you saw, that one had, I think, if I go back to it, it had 10 per case, and it had 3 times 3 times 3, so it had 18 different observations, each with 10. The ones I've done, I'd say as long, it's all got to do with the resolution. If you only have 10 data points, you can only get 0, 10%, 20%, 30%. I give you a feeling that you'd probably need 8 to 10 different groups, and each one with 10 or more in each group. And it really is a function just like all binomial or percentage work. The closer you are to 0 or 1, the greater amount of data you need to resolve the difference. If you're closer to 50% in a result, you don't need as much data. And it's got to do with the way the standard deviation is calculated in binomial data. So really, more data you need, the closer you are to 0 or 100%. I don't know if that's an adequate answer. I'm dancing around right now.
One other question.
Go ahead.
Clarify why a low P in one case denotes acceptable, and in the other a low P, I think they mean does not. Probably the framing of the H, null.
Good question. Minitab and all software doesn't care what the numbers are. It will predict either the highest P or the lowest P. You just give it pass and fail data. Most people choose to put in the one that's of most interest to them. In the second one, they were trying to find passes. The second example. The first one, they were trying to minimize failures. Now, what's the difference? You know nothing. But you put in the one you want, and the software will correct it. In Minitab in version 14, no matter which one you did, it seemed to always solve for the minimum, the closer to 0 value. And I never quite understood, but when you'd give it pass data and totals, or fails in totals, and it generally always solves to minimize failures. But again, the computer knows which are which, but the software doesn't really care. The transform or the link function just converts them to continuous data, so it doesn't really matter.
One more question. Is there an R-squared value for binary logistic regression similar to regression that allows explanation of variability explained in model comparisons?
Wow. Not really. That concept, you could probably estimate it, and it makes me want to go do it now, but if you did the logic function yourself, created that new function, you could run it through regular regression, and it will give you an R-squared. The logistic regression tool does not provide one. What you're really more looking at is, I'm going to go back a couple slides to the output. You can sort of look at it with the log likelihood value, which is somewhat equivalent to it. I really don't want to get into how to do it. It deals with the likelihood estimates of the parameters. They take the natural log, so it's normally distributed, and the smaller this number gets is equivalent to a higher R-squared. But that one took me a long time for my master's degree to figure out how it works, but that's really what it's sort of doing the same thing. If you wanted to compare different link functions and adding and subtracting predictors, you would compare the log likelihood for the smaller number would be better, meaning more negative. They're generally all negative numbers. Taking the natural log of a number less than 1 always gets you a negative number. So that would be the equivalent, but I don't have a thumb rule to convert that to percent explained. So no, there isn't the direct relationship. All right, good questions. Got to go back to my slide. I appreciate you asking, especially that last one. Never thought about that one, so it's going to drive me to go do something. All right, we're really wrapping up. That was the theory and the practice part. You might be thinking of other ways you might be able to use them. Great time to talk about where you might use them if you have questions. I found really any time I have discrete data that I really want to go analyze it with parameters. Now, when you think regression, you think continuous parameters, but you can use, discrete characters too. Now, before I go on and finish up some of the extra stuff, I would like another question to ask of you. Now that you've seen it, this is generally not part of the training black belts get. I know in our company we give it to black belts and master black belts, and we have a class that's called, we call it our graduate course. It's really like, it's the advanced analytical tools for a black belt, a week-long course, and we put it in there. But do you think this should be a standard tool given to black belts and should be in the black belt body of knowledge? And I gave you a couple tools there, or a couple choices. I'm interested in where you think on it, especially since about a third of you have actually used this in practice. Looks like the largest one is the middle choice, maybe, but it should always be a master black belt tool. And if you're not a Lean Six Sigma person, black belt is generally the practitioner that goes out and solves problems. Master black belts are ones who teach them and give them that extra level of support. It's probably the highest I've seen. We almost broke 50%. It should be a black belt body of knowledge, not necessarily a black belt one. Well, thank you for that. I do believe all master black belts should have this under their belt, if you want to say, with their possible tools. Because I'll tell you something, there's times that nothing else works. And if you find your attribute data, your percentage failure rates are all well away from 0% failure, you generally can get by with regression straight up in ANOVA. But this is really a better tool. It's like sharpening your skills a little bit, sharpening the pencil so you get finer lines such as that. So thank you for that. So what have we seen so far? This is the end. This is a summary to this point, that logistic regression, especially the binary case, can give you answers when you have an attribute output variable, KPOV being a key process output variable, where the input variables are continuous, which were all of my cases up to that point. Bonus material. This really isn't a bonus, but if you get and can accept that logistic regression will work, what you'll realize is you can use that analysis tool for other designs of data. And a key one I have used, even since I've been with Smarter Solutions, but creating the design of experiments like you would and have you been trained, but all you get out of it is pass-fail data. Well, you can design it in the design of experiments tools that Minitab and other software provide you. Get your matrix, run your observations, but instead of collecting a continuous variable, collect the count of how many passed and failed under those conditions. You take that matrix right out of design of experiments, and instead of going to analyze DOE, go take it to the logistic regression or binary logistic regression tool, and now you define your columns in your DOE as continuous or attribute. I'll show you how in a slide coming up here. And you get an answer of significance and, again, a predictive model with pass-fail data. This is really powerful because if you do it this method and balance the number of samples in each condition, you get a very good answer. Now, if I can do that, of course, I can do analysis of variance also. So you can actually do an analysis of variance without any continuous variables when your output is attribute. Now, I've been talking binary, but it also does nominal and ordinal. Even with that kind of data, you can both do design of experiments and nominal and ordinal logistic regression with both of these tools. Becomes powerful. I'm just finishing up one with one client using logistic analysis of variance to look at their employee surveys. When they have asked employees how they, on this question and that question, you may have had them or not, but it's very difficult to analyze in some cases, but we could look at regions and seniority and tools like that to look what's really driving the answers on a ordinal scale. I think they had 1 to 10. Usually I see 1 to 5, but they went 1 to 10. But again, you could predict what was driving the higher answers using logistic regression because they scored 1 through 10. And why this is important is when you get scales like that, those scales are relatively arbitrary. They're asking how you feel about it. The difference between an 8 and a 9 may be different than the difference between a 6 and a 7 or even a 1 and a 2. Since the spacing between them isn't equal, you really don't want to consider them as continuous variables. Now, in Minitab, and I'll talk about this, and I assume all software's got equivalency, how do you enter data? Well, you put your pass-fail data, this is binary we're talking about here, up in this section. This is where I put the continuous terms and the discrete terms. If it's a discrete term such as north, east, west, and south, you also list it here. So it has to be in here to be in the model, but by putting the same column in here, you're telling that it's also a discrete factor. Even though they call this regression, it will allow you to have a column up here that isn't numbers. They can be text. It will work out just fine. The output looks a little bit different. It looks more like an ANOVA output. In Minitab, it's sort of equivalent to the general linear model or GLM function, that if you have an attribute such as north, east, west, and south as a region, it will just give you a little different in your coefficient table, or it's the same as using indicator variables if you've ever tried that, which also, if you use indicator variables to map a attribute into continuous terms, that also works with this tool. Any questions on that about data entry? Okay, I'll get a question. I think 2 more slides and I'll ask general questions. So I really finished up the topics I wanted to cover today. We've been about 45 minutes. It looks like we're doing well. Hopefully you get a feeling for the flexibility of logistic regression. I would hope you'd feel comfortable to try the binary one. Again, I'm sending you the data sets. Since a majority of you wanted to brush up your knowledge, I recommend you copy that data set out and try it. See what you get. There we go. And if you want, you can try it on the other things. Now, again, great time for questions, situations you want to share with me. Now, Mallory, what do we have?
What is the proper logistic regression tool for non-ordinal predictors? Cities, categories, multiple attribute outcomes.
Okay, low. All right.
Low, medium, high, extreme.
Okay. Now, for low, medium, high, that is ordinal data. You treat them. Let me go to Minitab. Oh, I've got the thing set to be a highlighter. I've got to change it back to a mouse. Ooh, that's not the right one. I want regression. Now, if I go to ordinal, that's where I have to give it a response, which generally would be numbers or low, medium, high. And what you're doing is I really do think it needs to be numbers so that it gives them order. So if I use low, medium, high, I'd probably call them either -1, 0, and 1, but it's ordinal. Now, when I get to the other one, as in regions or cities, was part of that question. So I get back to regression. That's called nominal. Nominal meaning each category has a count, but there is no order to them. Not one better than the other. They just are like bins you sorted them into. In this case, you still have to have the responses. For each combination of settings, you tell it what bin they ended up in, or the counts per bin. So what I find is you enter the data that's got, it went into this combination, how many of them had low, how many of them had high, say north, how many were south, how many were east, and how many were west. If I go back to my slides, it was way early, let's say about 15, how the data form. Generally, you would probably enter nominal and logistic, the nominal and the ordinal data. It could be in this form here, where I have the response, which would be your ordinal or your nominal value, and then I have my factors. So each one, it either is a north, a west, an east, a south, or whatever. You have one row per observation. You tell it which bin or category it fell in. You can also use this format where you really, for each set of combinations, you've got how many went to this bin, how many went to that bin. I hope that answers it. Really, you still get p-values. I don't have an example to show you on it, but you look at the p-values, see which drives it, and the regression equations that come out of it would predict the percentage that end up in that bin or combination. I hope that helped.
Okay, the next question is, what are some guideline rules for deciding when to use?
Oh, I'm not even going to pronounce Hosmer, Lems. Okay, let's go back to my slide so I can pull the slide up that's got it.
As the primary indicator of goodness of fit.
Well, for goodness sake, I have looked for a while to find some guideline that tells you which one to pick, and I've never found one. It's the same as with the link functions. I can't find a rule that everybody uses to pick one. I found stuff on the logit to the probit, which is really a normal fit type thing, but it didn't make sense to me. Honestly, I would trust any of these to be acceptable. The same as when we use Minitab to test goodness of fit on normal, they give us 3 choices. You can use the Anderson-Darling, the Shapiro-Wilk, and they give you one more, the Smirnov-Kolmogorov. I probably pronounced it wrong. They're all considered acceptable. So I don't have a guidance on which one's better. I like the Pearson one because I understand it's really looking at the chi-squared goodness of fit test using Pearson's correlation method, which is one I understand. But they're all considered acceptable. I think I have made up my own statistical theory, the Rick Haynes theory of statistics. If any tool is named after a person, there's other ways that are equally acceptable to go do it. When there becomes a consensus across the world that this is the best way, it generally gets a generic answer or title. So I don't have a reason why you pick one or the other. Is there another question, Mallory?
Yes. How balanced should the sample size per cell be in logistic DOE?
For logistic design of experiments, I'd recommend for all design of experiments, you should try to get the same number of samples in every combination. It allows for what it does is it minimizes the uncertainty of your prediction, so it reduces the variation. Now, with any analysis, the more balance you get, the better the statistics works because you're distributing the uncertainty of prediction equally across all cells. Now, one of the odd things about logistic regression, it doesn't seem to give you a change in an output at all based on the number of samples in each combination. Like the one example had 12 in one setting and 37 in another. But you can't see that in the output, what the impact of it is. So I generally say the more balanced you have, the better you are. But in the real world, you don't get much control of that unless it's a design of experiments. I think what you find is if you have an unbalanced design, as in more samples in one than the other, what you get is it's the equivalent of the p-value is harder to achieve. The uncertainty of your estimate goes up, and you need a bigger difference to drive significance. But your best bet is always to balance them, but I would not fear going to this tool with a quite unbalanced equation. If you have one combination that has a small sample size, what you'll find is if it gives an odd answer, it'll show up on the equivalent of what I chose was the chi-square to the delta p, which is looking at your goodness of fit changes. You'll identify it as an outlier if you follow these tools and you go back and investigate it, maybe get more data. That's the best I have on that one.
Okay, our next question is, are there any other suggestions on graphing charting techniques when you have several significant variables?
Wow. As you saw, we copped out an example of only doing 2 at a time. And I think at some level you're lucky if all 3 of those charts, like we did on the pencil hardness thing, showed up to be pointing to the same direction. If you've worked enough in Lean Six Sigma, you'll find there are competing results. When you take one to its positive, it drives something else that's important down. For graphical techniques, you have you can do a 3-dimensional plot like a contour plot that's the 3rd dimension is in shading, but beyond that, I've never found one that I liked real well. The multi-vari plot works a little bit if you're going to search multi only on means because it'll allow you to go to it'll do 4 factors and show you the output of a mean. But again, you have to be a good visualizer to see the use of that. But no, I don't have a great tool. What I'd recommend, if you really get to that point, is you build the equation that came out of, use the coefficients, go to Excel or another math program. If you use Mathematica or some of those other ones, program the equation in and use the solver in Excel to solve for your optimal condition. And I would probably play with the variables and look how they respond because you can see from the coefficients what direction they drive the logit function. So you'll know if you want to make it positive or negative, you can see the direction as you move them. But you have to play with it. I don't have a good automated graphical explanation. If you have 5 factors, I guess your best hope is they're not all significant.
Okay, and the next question, what are the most typical misuses of binary logistical regression that we should avoid?
Boy, now I'm going to be a bit, I would call it humorous, you may not, but most people who misuse it never even realize the function exists, so they don't get a chance. The biggest misuse is the non-use of it in using a standard regression or such as that. If you can get the data in this format and accept your p-values, I don't know if you could misuse the tool. Now, I have seen errors in using it. When you go beyond the binary one and go to the nominal or the ordinal type, you have to be very careful when you're using your predictive equation to make sure you're predicting the right thing. So what I always recommend is when they take their equation and try to actually solve for each condition, they do an idiot check to make sure that it really is not solving for the defect rate or solving for the, you want to solve for the probability it ends up in that condition versus the probability that it doesn't. So you really have to go back and put the real numbers in and make sure it looks right. So other than that, I haven't seen many misuse because most people don't approach this until they're thoughtful to get there. Mallory?
Do the odds ratios provide value when interpreting results?
Yes. There's a tough one. Odds ratios are very difficult to teach and talk about. What they mean, excuse me, if the odds ratio is 1, what that means is 1 unit change in the predictive parameter doesn't change the odds of the output. And I don't have it really in this presentation, but what you really do is you take the odds of, if you change 1 unit in heat, how does that change 1 unit of output? And then we'd look at that as a ratio of the other choice. See, if I change 1 unit of heat, what's that change, the percent change of success versus the percent change of not being, or non-success, and it looks at that ratio. Now, I can understand it a little bit in a very simple analysis of variance case where there is, like if one of my factors was male or female, it's very easy to understand. It becomes very difficult to discuss when you have continuous parameters, how it's calculated. But in reality, what they're looking for, if you look at the odds ratio, it's the confidence interval to the right is how you use it. What they're saying, given the effect of heat in this case, the odds ratio comes up at 1.09. Now, it's got a confidence interval that says it could be between 1.04 to 1.14. That's indicating that 1 unit change of heat has this much effect in the odds of getting a success or fail. Now, if that interval includes 1, it means there's a chance that it does not have an effect. So you can almost treat it as like looking at the t-values in a regular regression. We're testing the null hypothesis. Does the t-value equal 0 or equal 0 for the coefficient? This is a little bit looking at the impact of it. So the farther away that confidence interval is from a value of 1, the more significant the parameter is. I really can't go past there talking without, I guess, moving my hands and getting equations out. I hope that's acceptable.
What are some steps you can take in order of simple to more difficult to troubleshoot the warning that the algorithm failed?
Well, like all testing, you should confirm it. I mean, I would hope whenever you do one of these that you go back and set up the process and run it and make sure it confirms the reasonable result. I do a bigger sample size on my confirmation run, but here's where your risks lie in doing this. All right? If none of the goodness of fit tests are acceptable, as in they're all less than 0.05, chances are you do not have a single process. You probably have more than one process going on. The same as I look at bimodal data of your project. So if you can never get these, at least one of them above 0.05, you're at risk of accepting your answer as being reasonable. That's probably the biggest thing I can say about, see, I'm going to go back and read the whole question again. But I think that's where, and the guidance is if these fail, go to the other linkage functions. I've never I don't do this all the time, but I've never had to go to the other linkage functions. The biggest, okay, so the one there, if you get past there, you try other linkage functions. If none of them give you a goodness of fit test that's above 0.05, I recommend not accepting your answer. So there's the first troubleshoot. I'd look at that there's more than one process going on. I generally recommend go to a demographic. Maybe you have to check each region separately because there are completely different processes going on. Or maybe you, in like all defect data, maybe you've mixed 2 different product types, or the defect, if I get into reliability statistics, is the failure mode changes, you get a knee in your probability plots for reliability data. The same thing could have happened. You might have had 2 different failure mechanisms going on and they cancel out. The other risk would come up when you look at these probability plots. I use delta chi-squared a probability, looking at as I add a data point in and out, does it dramatically change either the goodness of fit test, and this is using the Pearson goodness of fit test is really what it's plotting on the left, how did it change, versus the probability of what it predicted should go on. Now, in this case, there was 2 cases which were the 8th and 12th row, that they predicted a low failure rate, but the dropping of that point dramatically changed the goodness of fit, which means they are potential outliers. Your other issue in troubleshooting is if you get a few points that are way off this group, you either need to consider getting more data on those points to make sure they're real, because if it's a small sample, that may be a troubleshooting issue. You have to go collect more data there. But if they are way off, they may be the most important points, and you may not have a smooth process. That there may be a discontinuity that the yields fall off dramatically. Realize at some level we're assuming there's a smooth process, or the defect probability is a continuous process. But if it goes along and all of a sudden there's a combinatorial failure, that if A, B, and C factors are at a certain condition, it goes to 100% failure, and it's not predicted based on the other characteristics, you would see it in this plot. Or the other thought, when I go to this thing, if you look over here, Minitab's here's got 8 different plots. I'd probably plot through all of them, use the brush function, look where they show in the other plots, read about what they do, and troubleshoot them, because the bottom ones are all about high leverage rather than high residual equivalence. But that's about the best I can tell you on troubleshooting. All right, that's what we have right now. If there are more questions, I think you can put some in on the survey at the end. I appreciate it. Or email them in. I think you'll have contact information when we get the email from us. I'm going to go back to the end so I properly wrap up. There's my bonus material. We've covered this. Questions? So here we go. But please send questions in. I also run a blog of student questions and things that come from this. I plan on my blog today writing some of the neat questions you guys gave me so that people can read. You can get to it from our website. It's called the Practitioner's Blog. But I put interesting stuff. Generally, I book questions that students ask and what the answers are if I think they're generic in nature and not specific. If you choose to get the books, the Volume 3, the one on the bottom here, is the one that this topic came out of. But we give you a discount. There's a code here. You will also get the code in the email if you want to order the books from us later. I think they're also available on Amazon if you choose to go that path. But there's a lot in there. The Volume 3 is the one that really is about projects. The Volume 2, which is an interesting one, it's about using the Lean Six Sigma tools to do business-level analysis. But I do appreciate your time. Those were great questions. It shows that you paid attention. I really appreciate it. I learned from this because you guys asked me a question I didn't know the answer to, and we worked through it. But I will play with the R-squared issue. That was interesting. Appreciate your feedback again. Fill out the survey. Ask for more. We will be doing these practitioner-type topics somewhere about once a month as we get to them, as they get time. So I appreciate any feedback. If you have suggestions for topics, please send them along. Thank you very much.